Now we're going to get into equations that have more than just one variable. So what we're going to end up dealing with here in another little bit are equations that have two variables in them. And we're going to start by being more on the low-key side by not having any sort of crazy powers or any sort of crazy roots or anything else that is complicating what happens. We're going to keep it very basic. We're going to allow for multiplying with numbers and variables. We're going to allow for adding, subtracting, and arguably you could say dividing or some fractions. But we're going to keep it to those basics where the variable stuff is no more complicated than just a single variable and then another separate single variable. And what this does now is creates a bit of an issue for us in how to represent the relationship between those two different things. We would have to extend the view that we've taken in the past where we've said, look, regular numbers, slap them on a number line. Now we've got regular numbers for one variable, and then we've got a completely separate second variable. So the nicest thing for us to do to try to create a relationship between those is to have another number line that's now situated going up and down, or vertically. And that creates for us basically a grid. We call it the Cartesian plane or the rectangular coordinate plane or system, as it may be. And so what you have is the normal number line that we've been dealing with, because the most common variables that are used in these new equations are going to be x and y. We refer to that horizontal as the x-axis. We're slapping in an extra number line that's going up and down, it's going vertically, and so we would very often refer to that as the y-axis. And what that creates for us is 4 quadrants, and the labeling goes like this. The upper right, quadrant 1, and then we go counterclockwise, quadrant 2, 3, and 4. When we talk about moving, we try to take the sort of natural inclination. If we move up, there is a sort of natural, traditional, historical connotation that that is positive. So going up is positive, and then that means going down is negative. So we've got for our x, or whatever variable we have to represent that horizontal, the normal sort of situation, go to the right, positive, go to the left, negative. Throw in the new y, or whatever that label might be, depending on the problem. That second coordinate, negative and positive. So down is negative, up is positive. We also now extend a definition that we've had as well with equations that had only one variable. We talked about solutions, and we said that the solution to an equation with one variable would be a number that makes that equation true. Now that we're extending to an equation with two different variables in it, then we would have to have a pair of numbers that will work together to make that equation true in order for us to have a solution. So this is going to be a pair of numbers. Kind of danced around the idea here, but if the common labels are x and y, the common variables would be x and y, well, we need to know which of those numbers in our pair is the x and which one is the y. So we need to have an order. And that order is also going to help us in case we get the extra little twist where we have an equation that has not x and y, but two other letters in there for the variables. So for instance, in this very first example, just to mix things up and have things not be quite so obvious, the equation, took too long, the equation that we've got going on here, 5r minus 9q is equal to 23. If we want to put numbers in there based on this pairing, we need to know, is the negative 2 going to go in place of the letter R, or is the negative 2 going to go in place of the letter Q? Which of those would it be? Well, if we think about the normal x and y, and I've already given away that those are paired up, the x that we're normally used to working with for the horizontal line comes first, and the new part comes second. The order that appears there, I want to carry over to a problem like this one, where I have R and Q showing up. So the order that we have, X and then Y. Where would X come first and Y come second in what we would normally deal with? The alphabet. So if we look at any equation that has two variables in it, the most natural way of ordering those is alphabetical. Out of the letters, the variables, R and Q, Q comes first, which means the negative 2 is going to be connected to the variable, the letter Q. The positive 1 is going to be connected to the letter R, the variable R, and so we would put those into place to test that pair and see if it is in fact, just put those in the wrong spots. We would test those to see if they do in fact work together to create a true statement. Do we actually work this calculation out, 5 times 1 minus 9 times negative 2, and end up with positive 23? Well, we get a 5 plus 18, which is in fact 23. So what we would say about this particular ordered pair is that it is a solution so this pair works. Well, let's look at things with a different pair, but the same equation, 5R minus 9Q equals 23. Despite the fact that we have a different pair, the order of that pair still matches up with our variables. So the first number in our pair corresponds to the first variable letter as it comes alphabetically. So alphabetically, the first letter, still the Q. So the 3 goes in place of the Q, and the negative 4 goes in place of the R. And in this particular case, that means that we end up getting something that is not going to be a 23. So if that's not going to be a 23, then the point that we have in this part of our example is not. Technical difficulties. Technical difficulties, try to open that up again and see if we can get it working. Not. There we go. A solution. So, one other comment here about the way that I have phrased my conclusions. When we talked about equations with one variable in them, most often we found that if there was a solution, there would be only one. That while it's possible to have infinitely many solutions, it's not something that we necessarily come across a great deal. Now that we have these equations with two variables in them, it's actually now more often, or even you could say most often, that we get an infinite number of pairs that will make our equation true. So rather than saying this point, negative 2 comma 1, is the only solution, well, that's not true. It's not the solution. It's one of many. So it is a solution. This doesn't work It is not a solution. There are many others that don't work as well, but this is something that we actually have going on that's going to inform some more of our discussion when we get into dealing with these equations and connecting things up a little bit more thoroughly with the introduced graphing sort of idea of putting points on a grid and being able to draw what shapes these equations give us by putting points on a grid. Before we get into that though, there's a specific characteristic of these equations that we want to try to use to our advantage. And so the next part of the discussion here is about that particular feature, that characteristic, which is slope. The equations that we're dealing with are going to be, as we will see eventually, lines. And lines, being that they're straight, end up having this regular sort of traveling behavior. So when you're traveling along a line, you can easily travel in the same sort of way from one place to another, to another, to another. So if you're traveling on flat ground, you take one step, you take another step. There's nothing weird going on from one step to the next. If you're traveling though and there's an incline, you're also traveling in the same sort of way, and it's based on the steepness of that line. So you might have something that's a little bit more mellow, or you might have something that's a little bit steeper than that, or a little bit mellower than that. Or even, as opposed to the way that these diagrams appear, like this part of our switchback, we could have something that travels like so. We need a way of being able to distinguish between all of those different possibilities, which lines are more on the mellow side, which lines are more on the steep side, and actually the difference between those two kinds of lines, one that's steep in this way, so as we move from left to right, we're going upward, versus as we move from left to right, we're going downward. We need something that will allow us to distinguish between all those different possibilities. Slope is what's going to do that for us. And the most basic version of slope, the kind of one that has a little bit of a rhythm to it, is rise over run. Rise referring to how far we go up or down as we are traveling along that line. Run referring to how far to the left or right we go. We could take a little bit more disciplined approach to things, and this kind of matches up with a popular phrasing in science, the change in y over the change in x. Well, this idea, if we firm it up in terms of math, and the fact that we have points, pairs of numbers to work with, we can say, let's just designate a first pair and a second pair, and we can say if we start at the first point and travel to the second point, or if we travel from the second point to the first point, how would we be traveling? So we've got two different but related versions of the slope calculation or slope formula that we can use. We have the y of point number 2 minus the y from point number 1 as our numerator. We have the x from point number 2 minus the x from point number 1 as our denominator. Notice number 2, point number 2 info minus point number 1 info. We have to have that sort of thing matching up for our slope formula to work out correctly. And we can change the order on that and say that instead we could begin the top and bottom with the information from point number 1 and subtract the information from point number 2. It's a perfectly legit way of doing things. And for our first example of using the formula, we can actually use each of those and show that we do in fact end up getting the same answer. So let's use the points -1, 4 and 3, 11. Remember again that each of these has an order to it. The first number in our pair is going to connect with the alphabetically first letter. Well, in our formula, that means X. So each of those first numbers, got a little color coding there with blue. Each of the second numbers in our pairs color coded with green, so we can see how things work in each one of these formulas. For most of us, the popular formula is the one that begins with the y number 2 minus the y number 1. So the y, use my green, the y from the second point as it is appearing in the problem is the 11, and the y from the first point is a 4. The x from the second point is the 3, and the x from the first point is a -1. And so then we can go ahead and put our division and our subtraction in there. And because so often we see our negative numbers with parentheses around them, I'm following that same sort of tradition. Now we want to go ahead and simplify this. So up on top, 11 minus 4 will give us 7. And down on the bottom, 3 minus a -1 will give us 4. Now to prove that we get the same answer from using the other version of our formula, again, that one is just a rearrangement in the order that we put those numbers. So up on top, while we're still using the y numbers from our pairs, they appear in a different order, meaning that the y from point number 1 comes first, the y from point number 2 comes second, the x from point number 1 comes first, the x from point number 2 comes second, and we put our fraction bar and our subtractions in there. Now up on top, we would get a -7, and down on the bottom we would get a -4. But as we've done so often, we don't let the negatives stay in the denominator. We can also say a negative divided by a negative overall is a positive answer, so that this could be simplified more completely as the exact same answer we got originally, 7/4. Great. What on earth does this 7/4 mean for us? We're saying that slope has a meaning to it. It's a way of measuring the steepness of a line. So what is that actually telling us? Good question. With the answers that we get, very often they're fractions, and in fractions the bottom number is always positive. So my suggestion to you is to start out this way. Since the bottom number is always positive, and the very nice kind of rhythmic way of remembering slope is rise over run. If we run in the positive direction, well, positive is to the right. Our slope answers we can always view as beginning with the direction from our bottom number as going to the right, and in this particular example we have for our top number a positive number. So for our top number relating to that rise, that's either going to be going up or down. A positive would literally be rising in the normal definition of the word. So that direction based on our numerator would be up. So this is a way of sort of describing how we are traveling, that if we kind of mapped out the way that this looks, for every 4 steps to the right, we would go 7 steps up. Now we can take those directions, remember that they have opposites, and we can change those by reversing them. So that we would have left 4 and down 7. I can travel along this exact same line by doing either pair of directions. So if I go to the left 4 steps and down 4 steps, I'm going to be on exactly the same line as this set of directions has me traveling on. Or you could also look at it as whether I start at this point, -1, 4, and move to the other point, or if I start at the other point and move to the first one. I'm going to be on the same line, but I have a different motion, a different set of directions that I'm following in order to make that travel. So right 4 steps, up 7 steps, or left 4 steps, down 7 steps, one or the other. In fact, with certain kinds of problems, it might actually be necessary for us to look at the reverse set of directions so that we can do what we need to do. So we do want to keep this kind of thing in mind, that we have that flexibility when we're looking at things. Let's look at a couple of special situations here before we do a few other examples. The special situations that we have are the ones that are tied into those number lines that we're originally using as we're building our grid, our rectangular coordinate system, our Cartesian coordinate system. And that would be the normal number line we're used to, which is a horizontal line, and the new number line that we just threw in the mix, which would be a vertical line. What could we say, if anything, about the slopes for those? Well, our formulas can be helpful, and if we use the formulas and try to see how things play out, it turns out that horizontal lines do have a slope. There is an answer that comes from that slope formula, and the answer is 0. So we do have an answer. The answer is 0, so 0 slope. If we have a 0 slope, we have a horizontal line. If we have a horizontal line, we have a 0 slope. So we want to remember that connection works both ways. If we use the slope formula and we pick points that would be arranged vertically, then our denominator ends up, well, kind of exploding in our face. Our denominator ends up giving us a 0. Well, we're not allowed to divide by 0. And if we're not allowed to divide by 0, then we would say that that is undefined. The slope is undefined. That means that there is not a slope. There is not an answer that comes out of that formula. So we actually have one of the very few times where there is a difference in math between the idea of no thing and the number 0. So this is one of the only times that we've actually seen this sort of different understanding. 0. There is a slope. It is the number 0. There is not a slope. The formula does not generate an answer. The slope is undefined is maybe you might feel a clearer or less confusing way of trying to remember that association. So now, any vertical line has a slope undefined, an undefined slope. There is no slope. If there is no slope, if the slope formula is undefined, then we have a vertical line. So again, a connection there goes both ways in terms of how things are working out. So in these two special cases, we might want to just commit the extra slope information to memory rather than having to recalculate things again and again. We'll remember these two particular factoids for us whenever we might have a horizontal or vertical line that comes up in the course of our work. But most of the problems that we're going to be working are going to be problems that have a slope other than those special sorts of cases, like these. So in this first case, we've got the point 3, 0 and 0, 5. Notice that here I'm automatically defaulting to, well, the slope formula that I learned, which again is the one that seems to be the most popular one among students. The y from point number 2, which is a 5 in this case, minus the y from point number 1, which is a 0. That's for my numerator. For my denominator, the x from point number 2, which is 0, minus the x from point number 1, which is a 3. So on the top and on the bottom, we end up automatically getting a 5 over a negative 3. Not quite the appropriate answer. So we would either need to take the negative from the denominator and pull it out in front of the fraction, 5 over 3, or some folks prefer to actually take that negative and go ahead and move it up into the numerator. Now that we have a slope to work with, let's again just go ahead and emphasize what kind of directions this is telling us about how we would travel along the line. So first, we start with the bottom of our slope answer, because the bottom number showing up there is always positive, meaning that we would be traveling to the right, specifically 3 units, 3 steps. In this particular problem, the top number now is a negative number, which means that for this slope, we would be traveling down 5 units or 5 steps. And again, we can reverse this set of instructions, and the reverse would be that we would go left 3, up 5. So depending on the situation, we might be able to use the first set of directions, or we might actually need to know the second set of directions in order to work out what we need to work out. Similar idea here with the other example, having these different pairs to work with. Our formula is telling us again to start with the y from point number 2, which is a 4, minus the y from point number 1. And down on the bottom, the x from point number 2 minus the x from point number 1. This would end up giving us at first a 1 on the top and a negative 3 on the bottom, which, like we saw in the previous example, means that we would have our 2 choices of taking the negative and moving it in front of the fraction, or take the negative and move it into the numerator. Whichever one of these we are using, again, we start with that denominator, which is always positive, and in this case means that we would go to the right 3. And with the top number being a negative, we are going down 1. If we reverse this set of directions, then that means that we would be looking at left 3 and up 1. So one of the advantages here in having this example now is that we can take a little bit nicer look at the idea of slope and the steepness by just kind of mapping things out either in our imagination or with our hands and arms. Right 3, down 5, right? 1, 2, 3, down 1, 2, 3, 4, 5. So we get something that's like this. In this other example, right 3, down 1, we get something that's like this. So if you look at the way that I have my arms positioned, the first example here showing up kind of right above my head, it's a steeper line than then the other arm here, that's a little bit closer to a horizontal line, so a little bit mellower, so steeper versus mellower, or steeper versus shallower, you could say. So this gives us a little bit more direct comparison. We see what's going on here, that our slope is telling us that steepness, as opposed to our first example, which had us moving to the right and up, versus these two examples which have us moving to the right and down, we have a positive answer versus a negative answer that set us apart from those situations of, do we move to the right and up, or do we move to the right and down? So all told, our slope answers are taking care of all of those situations that we would want to know about, so that we can use that feature, that characteristic, to our advantage. This allows us to get into the equations of lines. So the different ones that we have, well, the nicest thing for us to start out with are those special ones that we were talking about a few moments ago as it related to the slope. We have the horizontal lines and the vertical lines. So because of the way that those things all are playing out, it turns out that every horizontal line is just simply y equals a number. No matter what number it might be, if there's nothing else going on, the y equals a number means that we have a horizontal line. Horizontal line means zero slope. So all we would have to do is identify where that y is, and we would actually be able to draw in that horizontal line. So as far as drawing purposes, that can work very quickly, as long as I remember that the horizontal line is connected to that key piece of information where my equation would have y equals a number, period. Vertical line, also simple in its appearance. The equation, simple in its appearance, turns out that vertical lines will always look like x equals a number. So again, we have that connection going on. Vertical lines do not have a slope. We could say the slope is undefined. They have the equation x equals a something sort of number, whatever number it might be, friendly or not so friendly. But again, those are special cases, and most of what we're going to be dealing with is somewhere in between the horizontal and the vertical. So how does the slope come into play? Well, one of the most popular versions of these equations is much like that earlier example where we just have our letters. There doesn't seem to be anything particularly special about the way that things are put together. Really, because there isn't. It's referred to as a standard form because it's kind of a standardized way of showing you, giving you an equation. It doesn't actually give you any immediate information that would be useful. So, not a big fan of the standard form. It doesn't have anything helpful that makes my life, our lives, any easier as far as handling things with these equations. Instead, if we had an equation that had the slope actually as one of the components, that I could either put the slope in or pick the slope out, then that would make things much more useful. And fortunately, we do have exactly that. We have this version of equations that's referred to as the slope-intercept form. So it mentions the slope, yay, we know about that. It mentions the intercept. Well, we'll get to that in just a little bit with a separate video. That we would have, for that particular sort of format, y equals a number, which would be our slope. Whatever number is showing up in between the equal sign and the x, that's our slope, the x. And then this plus b, this extra number that's at the end, either it's a plus something literally, or it could be a minus something, but that extra number in there at the end. Well, this particular format much more useful because, again, the slope is exactly whatever appears in between the equal sign and the letter x. Now, just as a little preview, the intercept that's mentioned is referred to as a y-intercept, and that's a specific kind of point, and that would be a second piece of information that comes from this format of the equation. So that means that this kind of equation would have two pieces of information that I can directly pick out. Or if I have those two separate pieces of information, I can put them directly in and build an equation for myself. So I've got a lot of flexibility there, but this is going to be by far the most useful version of the equations for us. Talk a little bit more about that in the following video. So just to kind of keep with the more major theme of slope over the past little while, let's look at an equation that's in standard form and try to work out the slope. Rather than trying to find points that might make that equation true, and once I get 2 points I can use my slope formula, that seems like a lot of work. If instead I use this now new version, if I was able to come up with y, talking too long again, if I was able to come up with y equals a number followed by x, possibly followed by another number being added or subtracted, if I basically solve for y and put things into just that nice, useful arrangement, then I can just go ahead and pick the slope right out and end up getting the answer that I need. And this actually would turn out to be, for the most part, far less work for us than trying to find 2 points for us to use in our slope formula. So we basically use our equation solving skills like we had done with equations that only have one variable in them. So if I look at things like, hey, I'm only worried about the y, I want to get that y by itself, what sort of little tools and tricks can I use to accomplish that? Well, firstly, we can get the negative 3y by itself by moving the 4x. In order to move the 4x, what we would need to do is subtract 4x on both sides. Because I know where I want my answer to go, what I want this equation to look like, what that means for us is that we're going to take that negative 4x and we're going to put it at the front before we write down the 12. So negative 4x would come first, and then the 12 is a positive 12. That means that we're going to add those two things together, so negative 4x plus 12. Again, because we know what we want our equation to look like, we want to have that y equals mx plus b. I want the x stuff to show up before I see the 12 stuff show up. Now the last issue to deal with is to get rid of the negative 3 that is showing up in front of the y. And in order to do that, we would need to divide on both sides by negative 3. Well, at first you might say to yourself, I'm going to go ahead and take all the stuff on the right side of the equal sign and divide by negative 3. But sadly, that's not particularly helpful in getting us to this kind of answer. I want a number that appears in between the equal sign and the letter x. And I want a number that shows up after the x. And I don't want there to be any big old fraction bar in there separating things, because that's not going to be helpful. It's not going to be useful. So this is not useful to us yet. We need to use a little bit of something we had in the past about division, which said, hey, you can take this negative 3 and put it underneath the first term, and take that negative 3 and also put it underneath the second term, so that these become separate pieces. When we do that, that means that we'll have the y followed by the equals. Then this negative 4x over negative 3, well, negative divided by a negative is a positive. And we said that what we would want to have is the number stuff completely moved out in front of our x. So the 4 over 3 we're going to have completely and totally out in front of the x. And then at the end, after the x, what we get from doing that simplification work is a negative 4, or we could say a minus 4. The part of this equation that we wanted to report was the slope, and the slope is the thing that appears in between the equal sign and the letter x. So the slope in this particular case is 4/3. So now we have a way of being able to rearrange an equation so that it is in a more useful form. That allows me to pick out not just one, but two important and useful pieces of information, one of which we've spent a little while talking about, the slope. The other one we're going to talk about a little bit at the beginning of the next video, and that is that y-intercept. So putting those two things together, we can have useful information. And because I keep mentioning being able to draw things, we're going to be using those two things to create drawings for lines so that we have a visual representation of the relationship that's going on